Hi there, this is True Socrates. Welcome to today's video where we will learn how to integrate rational functions using a process which is called partial fractions. So just to remind you, a rational function is simply a generalization of rational numbers where we have fractions of integers, but this time we have fractions of polynomials, okay? So we will have a polynomial divided by another polynomial, and we will integrate these functions. And you might say, wait a minute, we already saw examples of those, and you would of course be correct. We already know how to integrate these three functions, which are rational functions, because we know some integration techniques, such as making a u substitution. In the first one, make u x minus 3, solve for x, plug it in there, solve for dx, dx is just du. And then you probably have to split it into two terms, and you will use maybe the power rule, or maybe just the constant rule, and you will need the natural logarithm, which we saw a few videos ago. This one is also a u substitution, but yeah, it looks like you will only get 1 over u squared and 1 over u cubed. So you will need only the power rule from basic calculus. So even though the denominator, check it out, it's more complicated. It's a cube here instead of just first power. You can actually do this using just basic calculus, simple u substitution and the power rule. So just because an integral looks more complicated doesn't mean it's actually harder to integrate. This one is easier. This one is more complicated. So yeah, I hope that you recognize it as something related to the arctangent function. And by this time, you also know how to do a trig sub. So you can do either one of those, use the arctangent integral directly. Oh, but it looks like you're going to have to split it into two pieces. Okay, so one or the other. One way or another, you know how to integrate all three of these functions. But we are going to make it a little bit more complicated. Ooh, oh my goodness. So check it out. We will do these 5 examples. So what makes them harder? Well, there are now 2 different factors in the denominator here. So a u sub is not going to help you out. And here it gets even worse. You have a square here. So kind of like the cube that we saw in the previous screen. But now we have 2 squares. So both of the factors that we saw over here are now squares. So yeah, it's getting more complicated. At least it looks more complicated. This one is quite different. So we have something like, if the x plus 5 wasn't there, then we would know how to do this using the arctangent function or a trig sub. X will be 3 tangent theta, something like that. But that won't help with the x plus 5. Okay, that is definitely a deal breaker. And it gets even worse here, where we're going to square the x plus 5. Okay, so this is our agenda for today. We're going to integrate these 5 functions, and we will see what steps, what techniques we're going to need to do along the way. Okay, our first example, we have 3x cubed plus 2x squared minus 55x plus 2 all over x plus 5 x minus 3. I'm missing an x there, haha, dx. Okay, so what are we going to do here? Well, notice that the numerator is a cube, the denominator is a square, cubic and a quadratic, okay? So the first step that we'll have to do is we're going to perform a long division, okay? So in order to perform a long division, we're going to have to expand the denominator first, because we're going to divide this by this. We can't do it while it's in a factored form. So expand it out, we'll get x squared plus 5x minus 3x minus 15. Okay, so of course that's simplified to x squared plus 2x minus 15. All right, so this is one of those few times where I wish I was actually at the blackboard because it's a little bit difficult to typeset a long division in scientific notebook, but we will make do. So if you remember, you put the numerator on the right and the denominator on the left, and you put a bar in between to separate the two, okay? The quotient will go above this dotted line, okay? So speaking of quotient, okay, first quotient that we'll get, we're going to take 3x cubed and we'll divide it by the highest term in the denominator. So we're taking the highest term in the numerator divided by the highest term in the denominator. And of course, that simplifies to 3x, okay? So 3x is our first quotient. You can put it anywhere, but to me, it belongs above the x term. Okay, so we're going to get 3x, the first term in our quotient. We are now going to distribute 3x to the three terms in the denominator. Okay, so yeah, if they still teach long division in grade school, it's a lot like that, except we're doing polynomials. Okay, so 3x cubed will be our first term. Of course, it should be, because in the next step we'll be subtracting and these should cancel. 3x times 2x is 6x squared. So we'll put plus, plus, and 6x squared over here. And then 3x times negative 15 is minus 45. So we'll put minus and 45x here. Okay. So the next step is we're going to subtract the second row here from the numerator, the row above it. Whoops, sorry about that. Technical difficulties. Like that, and like that, and like that. So we're subtracting, okay? So 3x cubed minus 3x cubed, 0. You don't have to put down the 0. 2x squared minus 6x squared is negative 4x squared. Okay, so one more time, we're subtracting, not adding. Minus 55x minus plus 45x. So minus 55 plus 45 is minus 10x. Okay, don't forget, we're going to add the next term here now, which is the plus 2. Okay, so the plus 2 will drop down to that third line in the process. Okay, so our next term in the numerator is going to be negative 4x squared divided by x squared, same as before. So we will, of course, get negative 4. Okay, you can probably do this step mentally. All right, so a lot of times the highest term in the denominator is 1 something, 1x squared. So it's easy to divide. Okay, so that minus 4 will go into the quotient. So we have minus 4 up here. Next step, we're going to distribute the minus 4 to the denominator and put that into a new bottom line. So minus 4 times x squared. Again, they should cancel. Minus 4 times 2x, so that's minus 8x. Minus 8x. Minus 4 times minus 15 is plus 60. So we're going to get plus and 60. Ooh, that's a big number. But that's okay. We're not yet done. So we are going to get, when we subtract, that will be 0. You don't have to write it down. Negative 10x minus plus 8x. So we have minus 2x. And then 2 minus 60. So that is negative 58. All right, there you go. So this is our quotient. This is our bottom line for now. Can we keep dividing negative 2x by x squared? No, not anymore. Okay. So we're going to get a 1 over x. So basically we stop the process when we have a constant left, or I should say when we have a constant in our quotient. That constant might be 0. Okay, let me qualify that. So basically the bottom line should have a power which is smaller than the highest power in the denominator. Okay, so x squared power 2 minus 2x power 1. So this tells us that we are finished with the process of long division. Okay, so just for a little treat, Scientific Notebook through Maple can do the long division for me. So compute polynomials and divide. Yeah. So here is the answer. For some inexplicable reason, it is in the wrong order. So we get 3x minus 4, which is our quotient. And you have minus quantity 2x plus 58 over the original fraction. Okay, so of course our answer is correct. What this means is that in the next step, instead of integrating the original fraction, we will integrate these 3 pieces. All right, so here we go. This is our original problem. We already said that through the process of long division, this rational function can be rewritten as a polynomial, simple linear polynomial, 3x minus 4, minus the remainder. So the remainder was minus 2x minus 58. We can take out the minus sign, sure. So that remainder still has to be divided by the original denominator, okay? Very important. It doesn't make sense that it's just minus 2x minus 58, okay? Because we already have 3x minus 4 there. Otherwise, we would be able to simplify. You have to include the denominator. Do not forget the denominator, okay? So, of course, it is easy to integrate the first 2 terms. So, yeah, let me copy this. So, we'll go up, minus up, and minus up. Okay, what are you doing? So, we have 3x by itself, 3x dx, haha, minus the integral of 4 by itself, dx. Okay, so we're just using additivity, breaking it up into 3 pieces, minus integral of 2x plus 58 over the denominator, dx. Okay, so we're basically just splitting up these 3 terms into 3 integrals. And of course, we know the first 2 are very easy. So we will get 3 halves x squared. Where's my fraction? There you are. 3 halves x squared minus 4x. And the last piece, minus integral of 2x plus 58 over x minus 3, x plus 5. Okay, so this is obviously the tricky part, okay? How are we going to do this? We are out of tricks. U sub is not going to work, and so on. Okay, this is where partial fractions come in. And what we're about to do is a little bit of magic. And that magic is math, of course, but it is something which is not done in calculus. It is done in a field of math called complex analysis. And I'm sure you've heard of complex numbers. What makes this work has something to do with complex or imaginary numbers. Even though everything is real here, we're keeping it real. And yet, to prove that this method works in general, and you saw that list of 5 problems, right? So there are some problems there that will result in imaginary numbers, even though we won't care about it. Okay, more on that later. So, to do a partial fraction expansion, we're basically going to convert this single fraction into 2 fractions. Okay, that kind of makes sense because we have 2 factors in the denominator. Okay, so that's 1 fraction and we will have another fraction. Okay. So the first fraction will have denominator x minus 3. And of course, the other one will have denominator x plus 5. Okay. So this is the simplest form of a problem that requires partial fractions, where you have two linear factors, two distinct linear factors. And what makes this work is that the degree in the numerator is already smaller than the degree in the denominator. Remember, that's how we knew that we need to stop the long division. Okay, so what's missing? What we have to do is solve for two constants, two numerators, so that this decomposition is going to work regardless of the value of x. Okay, so in other words, this equation has to be an identity. It has to work for all values of x. So how will we solve for a and b? Okay, so find a and b. Okay, well, one thing we can do is clear out fractions. Clear the denominators. Okay, so multiply both sides by x minus 3 times x plus 5, right? So on the left, you clear the denominator completely, but let's do the right carefully. Okay, so we have two fractions on the right. Each of them gets multiplied by this denominator. Okay, so multiply the first by that and the second by that. Okay, let's make some space here. So I wanted to show this step because, as you can see now, the x minus 3 are going to cancel from the first term, but the x plus 5 will cancel in the second term. Okay, so very careful. So x minus 3 is gone, x plus 5 remains. For the second term, x plus 5 is gone, x minus 3 remains. Okay, so we have an equation. Okay, so let's shorten it. 2x plus 58 must be equal to a times x plus 5 plus b times x minus 3. Okay, now let me show you the fun part. This equation has to work regardless of the value of x. Okay, and we can plug in any number for x and the equation should work. It should be true regardless of the value of x. Well, if we plug in 3, let's start with positive 3. If x is positive 3, then the second term is going to disappear. That's just 0 times b is 0. So we get 2 times x, so that's 2 times 3 is 6, plus 58 must be a times 3 plus 5, 8 times 8. Okay, so 58 plus 6, ooh, that's 64. So a must be 64 divided by 8, which is of course just 8. Excellent. So we have found the value of a. A has to be positive 8. Okay, great. So now, what about b? Well, we can play the same game. To make x plus 5 disappear, we can make x negative 5. So if x is negative 5, then we get negative 10 plus 58 will be 0 plus b times negative 5 minus 3, negative 8. Okay, so let's be careful here. 58 minus 10, so we're going to get 48. 48 equals negative 8b. And so b must be negative 48 over 8, which is negative 6. Okay, so those should be our numerators. So thus, we have solved our numerators. We can copy this, and a is going to be 8, and b is going to be negative 6. Yeah, all right. I can make Maple do this for me. So I can go compute. I'm sorry, I have to be up here. Compute polynomials And where are you? Polynomials, there you are. Look at, check it out, partial fractions. Ooh, there you go. 8 over x minus 3 minus 6 over x plus 5. Is that what we got? Yep. 8 over x minus 3 plus negative 6. Yeah. So we can write this as minus 6 over x plus 5. Excellent. So now we know how to do the integral of this third term. So we get where we stopped off. We can now replace this with this. So let me make another copy just so you see where it came from. I can change this fraction now to this partial fraction expansion. Haha. And of course, we know how to use the logarithm. Okay, so I gave you simple factors. So u is x minus 3, du is dx. Okay, so we can blatantly replace this with 8 over u du, and this one, slightly different substitution, 6 over v dv. Okay, watch the signs. So our final answer is going to be, the first term is a minus 8, so that's minus 8 ln of absolute value. Okay, I need absolute value bars. There you go. You're already set. Absolute value of x minus 3. And then minus minus, so that's going to be a plus 6 ln of the absolute value of this time x plus 5. Okay, so there's a small u substitution that you have to do for each of these terms, but you know how to use the natural logarithm. All right, first problem done. All right, second problem. So same denominators, the same factors, except one of them is now a square. Okay, but check out what I did with the numerator. I had x cubed before. Now it's down to an x squared. Okay, that's because I'm avoiding long division. Okay, you already know how to do a long division. So let's do a problem where we don't have to do a long division. Since the numerator has degree 2, which is smaller than 3, the degree of the denominator, we do not have to do a long division. Excellent. So we can skip that cell. We can go straight to the partial fraction decomposition. Now in the last problem, we only had x plus 5x minus 3, no square. So this is going to be different. And let me show you what the setup should be. Okay, so yeah, let's write it as setup. Okay. As before, we will have a fraction for the x minus 3. Okay, so first term, and let me make copies of this because we're going to need a few. So the first term will have x plus 5 in the denominator. As before, we're going to have x plus 3 as a second term. I'm sorry, x minus 3. Watch the signs. But there's a square. So when that happens, you must include a second term. But this time, instead of x minus 3, we already have that, we will have x minus 3 squared. Okay? So you got to remember this. When a linear term has an exponent, okay, it's called a multiplicity. So this has multiplicity 2. You should have 2 terms. Okay? And of course you can extrapolate. If that's a 3, then you will have a third term that has x minus 3. And this time it will have a cube. Okay? Fortunately, the numerators are still just constants. Okay? So we will have 3 unknown numerators, a, b, and c. Just go down the alphabet. Okay? And I like to use capital letters. So now, we must solve for the numerators. As before, we can cross multiply. We can clear the denominators. So on the left, you will have that. Let's go a little faster this time. Okay, so instead of copying this to all three terms, look at what's going to happen. X plus 5 in the first denominator will cancel with that x plus 5. So we will have x minus 3 squared remaining with the a. Okay? How about the plus b? Well, there is no x plus 5 there, so x plus 5 will survive when we cross multiply with the second term. But there is an x minus 3 there and x minus 3 squared there. So what should remain is a single power, degree 1, x minus 3. Got it? Pretend you said yes. Okay, now plus c. So this time x minus 3 squared is going to cancel completely with this x minus 3 squared. And so x plus 5 is going to remain. Okay, excellent. So now, as before, we're trying to solve for a, b, and c. And what did we do? We plugged in some special numbers. Okay, we can do the same, except we only have two good numbers to plug in. 3 and negative 5, just like before. So let's try. If x equals 3, we get, so it's going to be a little bit more complicated on the left because, yeah, we have a square now. So that is 3 squared is 9, 27 minus 44 times 3, and then plus 153. Okay, so I'm not going to pretend I can do that in my head. I'm going to press the equals button here, and that is 48 on the left side. Okay, so we get 48 equals what is going on the right. X is 3, so that's 0. This is also 0, so only the c survives. So we get c times 3 plus 5, and 8. Okay, so c equals 6. Okay, we got the number like that before. Okay, so yeah, 48 divided by 8 is 6. Excellent. So we have c is 6. We know who you are. You are 6. Okay, so let's try the other one. If x is negative 5, we get, so on the left, you get 3 times 25, right? So 3 times 25, negative 5 squared, minus 44 times minus 5. So plus 44 times 5, watch those signs, and plus 153. Okay, so that is equal to 448. Wow. On the left side. And on the right, so let's make some room here. Scoot, scoot. 448 equals, we're plugging in negative 5 on the right. So A survives, B goes away, C goes away. So even though we know who C is, it still goes away when we plug in negative 5. So we get 8A times negative 5 minus 3, which is 8. Whoops. Heist minus 5 minus 3 squared. Yeah. So this is equal to negative 8 squared, 64A. So A must be 448 over 64. Do we get a nice whole number? I believe so. We are gonna get, yep, 7. Okay, so yeah, not gonna lie to you, I rigged the numerator so that we get nice integers in the 3 numerators. Okay, 6, 7, both numerators. We are missing B, unfortunately. Oh no, what are we gonna do? Well, what have we got? We already made a lot of progress. So we have this, so far we have. Okay, so we know that A is 7. So A is 7. We don't know B, but C we know is 6. Okay, so we're missing B, We can't plug in 3 or -5 anymore because b will disappear either way, so that doesn't help us. Okay, well, what can we do to solve for b? I believe that the simple thing to do is to compare coefficients. Okay, we have 3 coefficients to play with: 3x squared minus 44x plus 153. Okay, remember this equation has to be true no matter what value of x you plug in. Okay, so when you expand this out, you'd better get 3x squared as the first term. Okay, so compare the x squared terms to get b. Okay, so yeah, and one more thing. We know this is useful because there is an x squared term times b. Okay, if there is no square here, there's no point in comparing the x squared. Okay, because b is going to disappear. Okay, so we will get 3x squared on the left side. On the right side, we have another x squared here, 7x squared. And then the middle term, as we said, gives you bx squared. And the last term, no x squared. That's okay. So it looks like b has to be -4. Okay, so that should be our complete right-hand side. Okay, so let's just put that over here. And b should be -4. Okay, and we can ask Maple to check our work for us. So I'm going to do it in a different way. Let's see if this expands correctly. Okay, so I'm going to go compute and, oh, you can see it there, expand. Okay, 3x squared minus 44x plus 153. Of course, that's correct. All right, so now we go back to our original decomposition. We have the numerators. A is 7, so we change this to 7. And then B is -4, so we can write minus here and 4 up there. And C is 6, so we have plus 6 over there. Okay, so there you go. That is the partial fraction decomposition of our problem. So now we will integrate, once again, term by term, by expanding this into 3 integrals. Okay? All right, so this is similar to what we had in the previous problem, except I think we had 8 minus 6 or something like that. Oh, the 6 is not where it was before. It's above x minus 3 squared. Okay, so the first to integrate like before, 7 ln of x plus 5 minus 4 ln of x plus minus 3. Okay, it's the last term now, which is slightly more complicated, but again, don't let looks fool you. That's just a u substitution as well. So u will be x minus 3. You have 6 over u squared, power rule. 6 u to the minus 2. Add 1, you'll get u to the minus 1 over minus 1. So we did that all in our heads. We're going to get 7 ln of absolute value. Here we go again. Absolute value bars of x plus 5. And then minus 4 ln of absolute value of x minus 3. And we said that we will have plus 6 u to the minus 1 over minus 1. So it's going to be minus 6 over u, but u is x minus 3. So it'll be minus 6 over u minus x minus 3 rather. So we just erase, go away, erase the squared. That should be our final antiderivative. Shall we ask Maple, did we do it right? Did we get it right? Did we get it right? So, equal sign. Where is my execute? Oh my, ooh. So we have, ooh, check it out. But it's cheating. It has an x minus 3 here. Yeah, and it's shared with all the terms. So yeah, sometimes Maple does not exactly give us an answer that looks nice, okay? So, but we do see parts of it. Minus 1 over x minus 3 times 6, that's a minus 6 over x minus 3 squared, okay? Look at the x plus 5s, okay? We have 21 minus 7x ln of x plus 5. In what universe does that make sense? Well, it's because we can put that together. We have 21 minus 7x, but we are multiplying everything by negative 1 over x minus 3. Okay, so it's trying to be, I don't know why it does this, okay? So we can obviously factor out a 7 here, or better yet, a negative 7. And then that will be times x minus 3, right? And then multiply by negative 1 over x minus 3 over there. So the minuses cancel out, and we will get positive 7. X minus 3's cancel out. So that's exactly what we have over, it's x plus 5. Yeah, it'll be 7 ln of x plus 5. That's what they have in common. Okay, so it looks like our answer is also correct. Okay, third of 5 problems. Whew. So, something similar from the last couple of problems, except this time both of them are now squares. Okay, so you can probably guess that, well, since we had 2 terms here for x minus 3 in the last problem, there should also be 2 terms for x plus 5. So, our decomposition will look like, what's that? 2 for here, 2 for there, so that's 4. We're going to need a 1, and 2, and 3, and 4. Okay, 4 terms. The first one will just have x plus 5 in the denominator. Second, the square. Okay, and then the third will be x minus 3. And the fourth will be x minus 3 squared. Okay, so the numerators stay just plain constants, a, b, c, and d. So now we have 4 unknowns, 3 before, and once again, we will clear fractions, the denominators. So left side simplifies to that. Okay, so who will go with the a? X plus 5, there's an x plus 5 there. So one of the x plus 5s will survive, and both of the x minus 3s will survive. So you know what, I'm going to copy this, and I will just cancel that power. Okay, for b, x plus 5 squares will eliminate completely the x plus 5 squared, so only x minus 3 squared survives for b. C, x minus 3 will cancel one of the x minus 3s. Both of the x plus 5s will survive. So 1, x minus 3 will survive. And for the d, x minus 3 squared will cancel with that x minus 3 squared. So both of the x plus 5s will survive. Okay, so again, plug in nice numbers. We only have 2 nice numbers to plug in. We have 4 unknowns, so we have to be clever with those 2, the other 2. If x equals 3, then what do we get? 5 times 3 cubed, 27, plus 42 times, 54, sorry, 54 times 9, and minus 59 times 9, and minus 892. Oh my. And we get, how much is that? Negative 802. Okay. But what's gonna happen on the left side? That's what we get. And on the right, we are gonna get. Who will survive? 3, 0, 0, 0. Okay, so only D will survive. So we will get D times negative, 3 plus 5 squared. Oh, 8, so 64. 64D. So is that going to give us an exact answer? Negative 802 divided by 64. What have we got? We got an ugly fraction, and that's because what was the mistake? I have 2 9s here. No, the minus 59 is just x, so that should be a 3. Okay, not squared. So what is this now? Minus 448. Okay, so minus 448. And we said only D survives. D times 3 plus 5 squared, 64. And so B must be, and this one should work. Famous last words. Minus 448 over 64 gives us, minus 7. Okay, so again, I rigged this problem so that all the numerators will come up to be nice integers. There's nothing wrong with fractions. It's just, ugly. Okay, so that is for x equals 3. And now if x equals minus 5, we get, okay, so careful this time. Why don't we just do this? Let's copy this. And then we plug in minus 5 cubed. And 54 times minus 5 squared. 59 times minus 5. Let the machine do the work for us. So what is the outcome? 128. And on the right side, who survives? So this time, x is minus 5. 0, not 0. 0, 0. Aha, so B survives this time. So that kind of makes sense, okay? The D term has the square, so this time it's the B term that has the square. So x is minus 5, so we get minus 5 minus 3 squared minus 8. Oh, we got 64 again, and yes, 128 divided by 64 is 2. B equals 2. All right, so we have 2 numerators. We are missing the A and the C. Okay, so let's do what we have so far. So far, we have copy and B is 2. So that is a plus 2. And D, what was D again? It was minus 7. Okay, so we have minus 7. Okay, so now we need to solve for A and C. Okay? We still need A and C. So we cannot proceed until we have those numbers, although you could perform the integration with just the constants missing. You might get extra credit or partial credit for that. Okay, so what can we compare? Well, I think cube is good because we have x cubed here, right? That's a square and that's a times x to the 1. So we'll get ax cubed here. There is no x cubed here. There is no x cubed here, but there is a cx cubed over here. Okay, so comparing the x cubed, coefficients, we must have So 5, I'm not going to write the x cubed anymore. 5 equals a plus c. Okay? No need to write the x cubed. All we are interested in is the coefficient. The 5 there, the a here, and the c here. Okay, so that's nice. A plus c must be 5. Okay, I need another good term to compare with. Okay, so is the x squared gonna be good? Yeah, I guess so. Because there's probably an x squared term here lurking, and same over here. Okay, so yeah, comparing x squared, except now we need to expand. We must expand. So we get, yeah, so we know how to do this. So I'm going to write that here, but x minus 3 squared is x squared minus 6x plus 9. Okay, so you see what I'm doing, okay? All I need is the x squared term. So the x squared term is 5x squared minus 6x squared. Okay, you see it? 5x squared here minus 6x squared. No other combination of a term here and a term here will give you an x squared. So this is a minus x squared. Okay, so how about, yeah, here you'll just get x squared. Here you'll also just get x squared. So this one we have to work for. And we just have to be organized. So x plus 5 squared is x squared plus 10x plus 25. Okay, times x minus 3. So the x squared terms, we're gonna get x squared times minus 3. So that's minus 3x squared. And then 10x can multiply by x to give you plus 10x squared. Okay, all we care about is the x squared term. Okay, I don't need 25x, I don't need minus 30x, minus 7. We don't need any of that stuff. So we get 7x squared there. Okay, so now bring in the coefficients. Okay, there's an a here to go with this minus x squared. Okay, so this we expanded over here. So we get minus x squared, we get minus a. Okay. The second term, we have x squared times 2, so plus 2. And then the third, we expanded it over here, and we get 7x squared. So we'll get plus 7, 7c. Okay. And the last one has x squared and minus 7, so minus 7. Okay, so that must be the x squared equal to the coefficient on the left, which is 54. Okay, so we get, let's clean that up, negative a plus 7c plus 7c equals, okay, so what have we got? 2 minus 5 minus 7 is minus 5. So 54 plus 5 must give us 59. Okay, great. But there's more. We know that a plus c must be 5. Okay, so what are we gonna get? Yeah, okay. We also have a plus c equals 5 from our previous equation. So, excellent. We now can use the method of addition. So minus a plus a gives us 0. Nice. 7c plus c gives us 8c. Systems of equation. Equals 59 plus 5, 64. Ooh, so c equals 8. All right, so C is 8. And from here, of course, what have we got? A equals 5 minus 8, which is, of course, negative 3. Okay, so we have our 4 coefficients. Okay, so I went to our work from above and I cut and pasted where we started. Okay, so this is the original function we're integrating. This is our decomposition. And we already solved for D and B. So I wanted to copy this part so that we know we have found everything. Okay, so D is 2. Get over there. And D is minus 7. So we have minus 7 over there. And we just found A is negative 3. And C is positive 8. Okay, so there we go. We will declare this problem as finished because, like before, we know how to integrate each and every one of these terms. Minus 3 ln of that plus 8 ln of that. U substitution, you'll get u to the minus 2. Again, that integrates to u minus 1 over minus 1. You know what to do. Okay, we will declare this problem done. Move on to the 4th of 5 problems. 2 more to go. All right, so now we are entering the next level. Previously, we had x minus 3, x plus 5, maybe you have a square. But this time, we have something very different. Okay, so we have x squared plus 9. This does not factor anymore, at least not over the real numbers. If it were x squared minus 9, then we will have x plus 3, x minus 3. That's a plus 9. So this is the important part. Important observation. Okay, the roots of x squared plus 9 are imaginary numbers. Okay, you remember your I. X has to be plus or minus 3i. Okay, remember I squared is negative 1. Okay, so when that happens, we have a special name for that. X squared plus 9 is called an irreducible quadratic. Okay, you cannot factor it further. In other words, at least not using only real numbers. Okay, so when this happens, we get a different setup. Okay, so what is that setup? Well, we still have the x plus 5 in the denominator. Okay, yeah, and by the way, if you're thinking, maybe let's try a trig sub, no, not going to work. Okay, so we still have x plus 5 here. But the good news is the x squared plus 9 is only going to give us one term. X squared plus 9 in the denominator. Okay, so in the numerator, you will have an a here like before, just a simple constant. What makes it different? Okay, there's going to be different in 2 ways. So x squared plus 9 stays as x squared plus 9, no power, no nothing. Instead of just a constant in the numerator, this is really, really important. There will be a linear term and a constant term. Okay, so not just one constant. Big difference. Okay. Now, maybe I'll just say something about this, that, well, in the past, we could have a square there, right? Putting that square makes the problem a lot harder, because you will have a second term. I'm sorry, a third term, one more term for the x squared plus 9. This time, as you can imagine, it will be a squared. And then the numerator will have what's next in the alphabet, dx plus e. Okay, so we're going to have 5 unknowns thanks to that square. And guess what? You can only plug in -5. That's the only nice number that you can plug in. The rest is, okay, I'm going to expand the numerator. It's one big holy mess. Okay, so That's all I'm going to say. You can have a square, and I hope for your sake that you never see a problem like that. I don't give problems like that because this is hard enough as it is. Okay, so again, we have to solve for the numerators. Okay, so clearing the denominators equals. Okay, so maybe this time, let's slowly do this. So each term gets x plus 5, x squared plus 9, okay? First term and the second term. Okay, let's do it slowly. So who survives with a? X plus 5 cancel, x squared plus 9 survives. Okay, and this is part of why I want to do this slowly. Okay, because in the second term, you don't have a single constant. Okay, you have bx plus c, big difference. X squared plus 9 still cancels out. X plus 5 survives. Okay, so let's make it shorter, shall we? So let's copy this and let's cut out the middle part. Okay, there you go. So that is the equation that we must solve for a, b, and c. Okay? And again, there's only one good number we can plug in, -5. If x is -5, then we get, so 10 times -5 squared, 25, plus 31 times -5, minus 31 times 5, plus 7. And this is equal to 102. And on the right side, the second term completely goes away, both b and c, because that's a 0. We get 5 minus 5 squared plus 9. 25 plus 9, 34. So let's just do that. Equals 34 times a. So a is 102 divided by 34. Is that a nice integer? I think so. That is simply equal to 3. Okay, so that's great so far. We only got one thing, the a. Okay, so let's write it out over here. So a is 3. Okay, we are missing the and c. Okay, however, we have our coefficients, and do we really have to expand? Okay, I see a 3x squared here. There's only one x squared here, right? Bx times x gives you bx squared. Okay, so comparing, oops, what was that? Comparing x squared coefficients, we must have, this is really good, 10 equals 3 plus b. Okay, 10x squared, 3x squared, bx squared. Excellent. So b equals 7. Wonderful. So we are now just missing the c. Okay, and how are we going to get the c? Well, c is a constant. Okay, so how about c times 5? Okay, that's the only place where you will get a constant from this pair, c times 5. Everything else has an x. Okay, so on the left, that's the constant term. On the first term, we get 3 times 9, 27. Okay, so comparing the constant terms, okay, in other words, degree 0. Okay, we get, so 7 on the left, 7 equals, on the right, 27 plus 5c. So negative 20, right? 7 minus 20 equals 5c, and c equals minus 4. Yay! All right, so that gives us a, b, and c. Awesome. So let's go back to where we started. Whoops, too much. Where are we? I hate it when it does this. There we go. So we have this decomposition, and we know A, B, and C. A is 3, and B is 7, and C is -4. Okay, great. So this is what we integrate, and I am once again going to declare this problem done because we know how to do this. That's an ln. This one, you can do two things. You can do a trig sub now. Now it's going to work because the x plus 5 has been separated. Okay? So you could do x equals 3 tangent theta, plug that in here. You know the rest. Solve for dx, 3 secant squared theta, and so on. So let's move on to the last number because it's already an hour long. All right, saving the worst for last, so to speak. So I wanted to compare this last problem with the fourth one, the previous one. So what I did was, okay, now I put a square over the x plus 5. Okay, as I said, putting a square over here is going to make it astronomically worse. Okay, so let's keep it manageable. Worst case scenario, no, actually, you can make that a 3 or a 4. Yeah, that will also give you complications. Okay, so this is bad enough as it is. What are we going to do in the decomposition, in the expansion, partial fraction expansion? So we have an x plus 5 square here. So when the power is more than 1, it means you have that many terms. Okay, so you're going to have an x plus 5 term, but you will also have a square. Okay, so you'll have b over x plus 5 squared. So let's replace this. Okay, and then for the quadratic, you will get something that looks like this, but we just use the b. So change the letters. That will be a cx and a d. Okay, so that will be the setup for this problem. Okay, one more time. That's a square of a linear term, factor. So we have x plus 5 power 1, x plus 5 power 2. Okay. Irreducible quadratic, same as before. So we must have a linear term in the numerator, cx plus d. One more time, expand, clear the denominators. So the numerator survives. Now let's do it quicker. Okay. X plus 5 in the first one will cancel with one of these. X squared plus 9 survives. So for the first term, we can remove that square. Second term, x plus 5 squares completely cancels that x plus 5 squared. So only x squared plus 9 survives. Last term, cx plus d here. And then x squared plus 9 cancels with that x squared plus 9. And we have x plus 5 squared right there. Okay. So is it useful to plug in -5? Yeah, that cancels and this cancels also. So when x equals -5, we get, so yeah, remember what happened a little bit ago. X cubed minus 5 cubed, x squared minus 5 squared, or 5 squared. 48 times minus 5. How much do we get? 306. Okay. On the right side, minus 5, 0. Minus 5, 0. Only b survives. So b times minus 5 squared, 25 plus 9, also known as 34. So b, yay, equals 306 divided by 34. Do we get a nice number? And yep, we get 9. Excellent. So B is 9. All right, so let's copy this. B is 9. Okay, so now we're missing 3 coefficients. We need A, C, and D. Okay, so is x cubed a good term? What do we get? So 6 will be, there's only one cube here. From A, we will get x cubed. There is no x cubed here, so that's excellent. Is there more than one x cubed here? Well, that's x squared, and that's cx plus d, so that's only one x cubed. So A plus C must be 6. All right, great. So we don't have the D. So let's see. Remember how the constant coefficient really helped us out last time? So using the constant coefficient, we get, okay, so on the left, -4, but on the right, so constant, the only constant here is 9 times 5, 45, 45a. There is a constant here, 9 times 9. And we have 25 here. And there's only one constant here, so plus 25d. Okay, so that's good. And now, notice something nice. We get 45a plus 25d must be -4 minus 81 or minus 85. Okay, and that's good because all 3 coefficients are divisible by 5. So we can reduce this to 9a plus 5d equals, is that 17? Minus 17. Yeah, 17 times 5, 117 divided by 2 is 85. Okay, so that's good. We have a plus c and we have 9a plus 5d. So we just need one more equation that has the 3 variables. And we have to bite the bullet and pick either 52x squared or 48x. Yeah, I think so. But it's not too bad because check it out. How many x squares are we going to get here? Yeah, I think x squared is the better choice. I could be wrong. Maybe x is also good. You got x cubed, 5x squared, but you don't get any other x squared, 9x and 45. So you only get the 5x squared for a. Okay. Using the coefficients for x squared, we get, okay. So we get 52 on the left. Let's get some more space here. And on the right, so we said we only get 5x squared for the first term, so we get 5a. Okay, there's still that a. Okay, so it's not just 5, it's 5a. And then we have a b here, plus bx squared. And, okay, so here it's going to be slightly painful. Okay, so let's copy this down here. Okay, I never said it will be easy. So this will be expanding the square. We get x squared plus 10x plus 25. Okay? So look for the squares. We will get dx squared and 10c. Haha. 10c plus 10c x squared. Okay, so just be very careful. Make sure that we found all the squares. Okay, so we have dx squared here. The cx multiplies to 10x to 10cx squared. We don't get any other x squared. Okay, there is no square here. So the cx can only go with 10, and the d can only go with the x squared. Okay, so we have found it. Okay, so we are missing plus d plus 10c. Oh, wait a minute. We already have the b. So the b, yeah, we'll put that in a minute. So d plus 10c. It's like, why are there 4 of them? Yeah, because we found b, we said that b is 9. Okay, so b is 9. There we go. So that is our equation. And yeah, this looks good. So let's see, what is 52 minus 9? 43, right? So 43 equals 5a plus d plus 10c. Okay, so we have that, and we have our 2 other equations. So let's put them over here. And you know what? Let me put the 43 on the right side. It's more natural there. Equals 43. Okay, yeah, 52 minus 9 is 43. I don't always trust myself. Okay, so we have 2 more equations. We get a plus c equals 6. So let's write that in the natural order here. And we have 9a plus 5d in the natural order equals minus 17. Okay, so this is our system of equations. Yeah, this is the messy part of this method. Okay, when you have lots of numerators, lots of coefficients in the numerators, and you run out of nice numbers to plug in, you might have to resort with comparing coefficients, having to solve a system of equations. Okay, so with that, so let's see. This has only a and d, but this has a, d, and c, a, and c. So let's think of eliminating the c from the first one, okay? So we can do that using the first and the second equations. So that was my scratch word. You didn't see anything. So we have to multiply both sides of this equation, maybe by minus 10. So minus 10a minus 10c, and then minus 60. Okay, and now add them together. So adding these 2 equations, and of course by that I mean the corresponding sides. 5a minus 10a is minus 5a, and the d survives. And yeah, that's good, because this is not a multiple of this, right? So we're on the right track. The c's go away. That's what we wanted. 43 minus 60 is minus 17. Okay, so again, 43 plus 17 equals 60. So we have minus 60 plus 40 minus 17. Okay. So now, okay, I'm still just mentally checking my arithmetic. So now we have 2 equations in a and d. So we have that, and we also have 9a plus 5d is minus 17. The other one is minus 5a plus d is minus 17, okay? So that's not a bad thing, because we can multiply both sides now by minus 5, okay? So we will take this equation, and we want to get rid of the 5d here. So we'll multiply both sides by -5. Okay, and keep your fingers crossed. Multiply by -5, so that's positive 25 minus 5d. Negative 17 times -5 is positive 85. Okay, so we get, adding them together, like before, 34a equals 85 minus 17. And I think that's right, because we get, yep, 68. Haha. And so, a is 68 over 34, which is exactly 2. Woohoo! And from here, it's downhill. Okay, we have a, so we know that a plus c is 6. So, keep going. And c is 4. And last one, we got A, we got C. Where's the D gonna come from? Well, we can do it over here. Yay! Minus 5 times A minus 10 plus D equals minus 17. Whoops. So, let's just make sure. A is 2 minus 10 plus D, and minus 17 on the right. So D is minus 7 plus 10, negative 7. All right, so we got A, C, and D. And what was B before? B, we said, is, get back here. B is 9. Okay, so let's write that down. B is 9. Okay, so we have the 4 coefficients, and we are now ready to plug them back into our expansion. So let's take this, and let's plug in our numerators, and let's see how to do the integration. Term by term by term. Okay, that was from the last problem. Okay. So A is 2. We know how to integrate that. B is 9. We also know how to integrate that. Yay! C is negative 7. And D is plus 9. Okay, yeah. So yes, I will also declare this problem done because we know how to integrate this. That's an ln, power rule, and the u sub. Split this up into 2 pieces. One of them will have an ln, one of them will have an arctangent. Okay, I do believe this is one of the longest, if not the longest video so far. And we only have, I believe, 15 or 16 videos. More to come. But yeah, it is, of course, somewhat complicated. Okay, as we saw, changing a power, changing a numerator, that can easily add to the complications of a problem. So thank you so much for your patience. I hope you enjoyed the video. And until next time, I hope you enjoy the rest of your day. All right, bye.